right? What's that? Yep, okay. We should have expected that, okay. All right, so this is almost the last session. I want to talk a little bit about accelerated testing. How do we use the physics of failure background we have developed to try to design accelerated stress tests. And the reason for accelerated stress tests we've discussed many times. The whole point is that the electronics are supposed to survive several years in the field. You cannot test it for several years in the test when you're qualifying your initial designs and your initial product. So obviously you want to run some kind of accelerated stress test to verify your design and verify your processing within a matter of few weeks, at most maybe a couple of months. But the point is that you have to accelerate several years of exposure in the field to just hours to weeks to months in the lab. How do you do that in a controlled manner, predictable manner? And the second place where accelerated stress tests get used is even after products have been fielded. Many companies will continue to run accelerated stress tests on samples. Some people call it ORT, ongoing reliability test. Some people call it RGDT, reliability growth and development test. And the idea there is that you went to market relatively fast. You were under market pressures. You're never quite certain if you've caught all the long-term problems in your accelerated stress test. Number one. Number two, sometimes you're worried whether you accelerated the test a little too much because you were in a rush. So people will usually run longer-term accelerated tests even after the product's been shipped, just to see if for the second generation or third generation release, you need some minor tweaks in the product. And there's always ongoing changes in materials. There's always cost-saving moves, and materials get changed in your design. So there are ongoing reliability tests to see how good those materials are. Okay? So there are several points in the life cycle where accelerated stress testing is conducted. So I'll just put up that same flow chart we had in the morning just to remind you that there are accelerated stress tests in several of these locations: EV testing, DV testing, PV testing, and as I just added, there's ongoing reliability testing that often goes on even after the product's been shipped. The first lots have been shipped. Okay, and those are shown again graphically here. We've been through this chart once before. EV testing, DV testing, PV testing, and the size of the samples progressively grows. Here it's just handful, 5, 10, maybe about 20 to 50 pieces here, sometimes 100 to 200 pieces here. You're trying to get statistically a little more significant. So specimen lot size keeps getting bigger as you go further into the process. And just to remind you again, down here, the yellow boxes are trying to verify the white part of the bathtub curve. And the purpose of the quality assurance testing is to keep the red and the blues to a minimum. Okay? Okay, so how do you conduct accelerated stress tests? The simplest one is just time compression. So if you think of applications like this where the product's only going to be used a few hours in a week, well, a few hours in a day to a few hours in a week, to maybe even a few hours in a month, intermittent short uses, then there's a lot of downtime in the product in between. Well, there's a room for acceleration right there without having to raise the stress levels. If you just run the accelerated stress test 24/7, you have already compressed a week into a few hours, right? So that's just time compression. That's not accelerated stress. You're not accelerating anything. You're just taking the downtime out of the duty cycle, okay, product duty cycle. But there are many cases where you don't have that luxury. The product's going to operate for many hours a day in the field, so there you have to raise the stress levels. There's no choice, okay? So that's what we are trying to schematically show over here. Look at this graph. It's got stress on one axis. It's got time to failure on the other horizontal axis. And on the vertical axis is the failure distribution, the probability density function of distributions. So the way we read this is, let's say you look at this stress level, which is temperature, Kelvin temperature 406. Okay. Over here, the mean time to, so here's the distribution of time to failure. The mean of the distribution is here, so that's the mean time to failure, and there's some distribution around that mean. If you raise the stress level, in this case temperature, from 406 to 416, it fails a little bit faster, but again there's some distribution around that mean time to failure. And so on. You raise the temperature even more, stress even more, it fails even faster. So the yellow line, yellow curve, is through the means of the distribution, and it's basically trying to show the stress-life relationship. So that would be like your physics. So if you had a model to fit that yellow line, that would be a physics of failure model. Okay, and that's the goal in physics of failure, is to come up with these stress-life models to the point where the model constant are just material properties. Okay, you don't want to engulf your or enclose your design parameters in there. You just want to make them at the material level, make the models at the material level. The other thing I want to point out is these probability density functions are getting taller and taller and narrower. That's something we do observe. As you get to higher and higher stress levels, we tend to find that for the same failure mechanism, same material, same defect density and everything, same variability, the failures tend to get more and more clustered. That means higher stress level narrows the distribution between the worst and the best components. And that's why it's getting taller, because remember, the area still has to be constant. The area under the PDF is still 1 unity. So if the base gets narrow, then the distribution gets taller. Okay, so that's really the quest in physics of failure world, is to find reasonable models to describe those failures. And once you do, now you can develop an acceleration factor. So you can find an acceleration factor between 406 and 426 if you have a model. So that way you can run tests for this long in the lab, and then use that acceleration factor and predict what's likely to happen at lower stress levels in the field. Okay? Or in other words, put it another way, you can basically predict for every hour of testing in the lab, how many weeks does it represent in the field. Okay? Okay. So the question is, so obviously I want to accelerate the stress levels to fail in a short period of time and not have to test for a very long period. The question is, how much can I increase the stress levels, right? So the second thing I want to, well, before I answer that, what I want to point out is you're looking at time to failure. By definition, we're not talking about overstress mechanisms, which will occur whenever the overstress event occurs. We're talking about wear-out mechanisms, cumulative degradation mechanisms, where damage accumulates over time and eventually it fails. So those are the ones we're trying to accelerate. We're trying to accelerate the damage accumulation rates so it fails faster. So which means these are the ones we're targeting in accelerated testing. There's no question of, there's no time axis to this, so there's no question of accelerating time to failure. We're talking about these. So now the question is, how much can I increase the stress levels? And this is a debate that's rampant in the field. People get very nervous the moment you say, oh, I'm going to raise the stress levels and test it at an elevated stress in the lab. All the component suppliers and the designers and everyone gets very nervous. Whoa, wait a minute, what do you mean you're going to accelerate the stress level? The product was designed to operate at 85, and the spec says can't go above 85. How far are you going to go? So the idea is that you're going to accelerate it above your use conditions. If your use condition was 35, just to give you an example, and by 35, I mean temperature of 35 C, relative humidity of 35%. How much can you raise it? Well, certainly to 85 maybe, if that's a spec, but sometimes you can even go beyond, because all that the manufacturer means is that if you go above 85, then the product may not last as long as you expect it to last in the field. Oftentimes they do have a fair amount of margin, design margin above that. It's not going to fail instantaneously if you take it above 85, but it certainly won't last 5 years, right? So we do go above those spec limits sometimes, but very carefully. You have to look at the materials they've used, see if any of them have an overstress limit at 85. So what you really want to know is, where are the overstress limits of the product? So oftentimes that's not what's given in the spec. So when they give you the specs, most manufacturers will derate their overstress limits and give you a safe spec limit. So oftentimes we find we can go above the spec limit, but very carefully. So, so what we typically do in accelerated stress testing is first we run an overstress test. So if I want to run a temperature humidity test, I will keep stressing up my temperature higher and higher and higher until the part fails. That tells me what the overstress limit is. Then I design a test where I back away from that overstress limit and run an accelerated test at some level that's slightly lower. So the true limit of how far you can go is that overstress limit, and we talk about two kinds of overstress limits. One is what we call an operating overstress limit. That means if you go above that, the product may not electrically still function correctly, but it's not dead. That means if I reduce the stress values, it works fine again. But above that stress level, it doesn't, it's basically it's got to drift off its functional parameters, and it's not going to function satisfactorily. That is what we call a reversible or a soft overstress limit, because the product is fine again once you bring the stresses back. There is another set of limits, the red line, where if you go beyond that, the product, that's a destruct limit. The product basically gets destroyed and it'll never function again properly. So that's a hard limit. We can never exceed that, but it's sometimes okay to exceed the blue limit because that's a reversible. So some products have reversible limits, some don't. So you have to be careful, okay, when you're accelerating. Okay, so the blue line, the yellow bar over here. So this is this, well, that's not really the spec limit. That's where the product is going to operate in the field, okay? So the margin between the black line and the blue line is basically your acceleration margin available to you for the operating margins, and the hatched bars are the stress margins available to you for acceleration if you're talking about the destruct limits. So that's your accelerated stress has to be designed within that. It cannot be a stress smaller than that because that's your operating condition, okay? It has to be something higher than that. So this is the margin available to you. Now, if your product is being designed to operate very close to its overstress limits, then you have a problem. Then you don't have much margin available to accelerate the stresses for accelerated testing. So then you have to basically decide whether you want to go for a different part that has higher margins. And you also need to ask yourself that if you're operating your part that close to its overstress limits, is it really going to live as long as you need it to live in the field? That's very questionable. Okay. Okay. So so in order to increase the stress limits, or when you increase the stress limits, all of the relevant failure mechanisms will start to accelerate. They'll accumulate damage faster. Okay. So let's look at some examples. I'll skip over this one. So basically, you're trying to accelerate all of these failure mechanisms by raising temperature, mechanical stresses, cyclic range of temperature, temperature rates, power, meaning electrical power, and harsh chemicals in the environment. So those are basically the drivers we use to design accelerated stress tests. So what kinds of models get used? Well, if you look at, so I've only talked about one model in the morning. Well, I gave you a table of models without giving you the mathematical form. The only mathematical form you've seen is the fatigue model. So here are a few more now. I'll go through several in the next few charts. So this is all mechanisms that are dependent on just temperature, max temperature. So you get this kind of dependence on temperature. This is the Arrhenius dependence on temperature. Time to failure scales with the inverse of the temperature, well, exponential of the inverse of the temperature. And the temperature, of course, is in Kelvin scale. So if you raise the temperature, time to failure drops. So there are quite a few of these failure mechanisms that respond to that kind of temperature acceleration. For example, creep accelerates that way. Stress-driven migration accelerates that way. Electromigration accelerates that way. So there are quite a few mechanisms here that accelerate with corrosion accelerates that way. Quite a few here that accelerate as per this equation, okay? As per this equation. So if you want the acceleration factor, you basically, what you're trying to do is the time to failure in the use condition divided by time to failure in the test condition is the acceleration factor. So if you divide one by the other, so if I do that here, so TUs is A naught e to the power activation energy. EA is a material property, okay? That's a material property. And that's called activation energy. It depends on the material and on the failure mechanism you're talking about, okay? Over Boltzmann's constant, that's just a physical constant, Boltzmann's constant, and T. So this T is the use condition, temperature in the use condition, divided by time to failure in the test condition. That's the acceleration factor, divided by same A naught, e to the power, same EA, same Boltzmann's constant, but now T of the test, temperature used in the test. So this could be 35 degrees C as an example, this could be 85 degrees C, and so on. But mind you, this is not the ambient temperature we're talking about. This is the temperature at the failure site, okay? Okay. And you may have to do some amount of thermal analysis to find out what that value is for a given ambient condition. So this cancels out, and you're left with e to the power EA over K, 1 over T use, minus 1 over T test. Okay? So that becomes the acceleration factor. So if you go back to the screen, oops. Okay. If you go back to the screen, that's the equation you're seeing over here. EA over K, 1 over T use minus 1 over T test. Notice that the A naught got canceled out. So there are two material constants here, A naught and activation energy. The A naught got canceled out, so you're dealing with only one material constant for that failure mechanism, just the activation energy. Okay? So dealing with acceleration factors is a little bit easier because you need less knowledge about the material. You need less material constants. Okay, here's another example. So there are many models for dielectric breakdown. One of the simplest ones is what we call an airing relationship. Like the Arrhenius, it is an exponential relationship, but there's no temperature here. This is voltage, okay? So voltage is appearing in two places here, 1 over V here, so it's V to the power minus 1 here, and in the exponential row. So that's typical in airing relationships. It appears in two places. There are two functions, okay? So here again, you can get an acceleration factor, right? So this would be, I'll write this down also. So it'll be T is 1 over V, e to the power minus A minus B over V. A and B are material properties, okay? V is voltage, so now time to voltage in the use condition divided by time to failure for voltage in the test condition would simply be 1 over V in the use condition, e to the power minus A minus B over V, V use, divided by 1 over V in the test, V in the test. So now this, sorry, that doesn't cancel, my bad. That's V test divided by V use, e to the power minus A minus B over V use minus A minus B over V test. And the A cancels out. You're left with B over V use minus B over V test. So once again, one material constant got canceled out. You're left with one material constant. Okay? Okay. Let's look at fatigue as an example. We saw in the morning that the Coffin-Manson power law uses a Coffin-Manson fatigue model uses a power law model. That means the cycles to failure is related to the cyclic range of strain at the failure site. Once again, there are two model constants there. One is the leading coefficient. One is the exponent in the power law. So if you draw the SN curve, fatigue curve, this is the slope and this is the intercept on a log-log scale. Okay, and now you can easily get the acceleration factor. This is cycles to failure under the strain in the under the strain in the test condition and strain in the use condition. This is cycles to failure in use, cycles to failure in test. So when you divide one by the other, you get this relationship. Once again, one material constant canceled out, one material constant stays in the relationship. Okay. Okay, so temperature cycling, oftentimes people will make an approximation. They will assume a linear relationship between the temperature range and the strain range. And for the Engelmeyer model that we discussed in the morning, that is true. Okay, so if you look at that, go back and look at that model, the strain that we calculated in the solder was linearly proportional to the temperature range. You can see that here. Let's open morning's presentation. Okay, so here's the IPC model. So you can see the strain is linearly related to the temperature cycle, range of the temperature cycle, range of strain, linearly proportional to range of temperature in the simple model. In reality, it's much more complex. If you were to do a finite element analysis and look at it and vary the temperature range, this wouldn't vary linearly. It would vary fairly in a complex way in a nonlinear manner. Okay? But this is kind of a zeroth order simplified model. And for a model like that, this relationship holds good. For a simple model like that, you could simply write this as linearly proportional to temperature. Same with the bottom. All the other constants in that relationship would cancel out. All the other parameters would cancel out. You'd just be left with the ratios of temperatures. So if in the field there's a 20-degree swing, and in the test you have a 80-degree swing, you will get a factor of 4 raised to the power b. B comes from the fatigue curve. Okay, 4 raised to the power b would be your acceleration factor. Okay. Okay. Same thing in vibration. People basically look at the excitation profile and look at the GRMS. So they make some simple models like this, the GRMS in use, GRMS in test. Everything else they're assuming cancels out because they're assuming that the strains are linearly proportional to the GRMS that you're applying for the vibration excitation. Unfortunately, again, just like temperature, up to a zeroth order approximation, you can get away with it, but gets very complicated very quickly because it depends on what kind of a power spectral density you have in the field. That means at what frequencies is the board being excited in the field, and then you look at in the test what frequencies are you using to excite the board in the test. So it's not just the GRMS, but it's also the frequencies at which you're exciting. If they're not identical, then you cannot make this relationship identical, make this relationship linear. Only if the power spectral density is identical, all you're doing is increasing the magnitude of the power spectral density, then yes, then it applies. Okay? And the reason I'm saying it's not POF is because of those nonlinearities that have been ignored. I'm just saying that be careful. These are oversimplified POF models. Okay, let's take something slightly more complicated. So here we had only one stress playing a role, temperature. Here we had only one stress playing a role, vibrational excitation. Here we had, which basically boils down to strain. Strain, only one parameter playing a role, strain, okay? And same thing here, only one parameter played a role, temperature, and here only one parameter played a role, voltage. What if there are multiple parameters, like temperature and humidity, okay? So if your failures are driven both by temperature and by humidity, then what does the acceleration factor look like? So here's a typical example, creep. Okay, we looked at some models for creep in the morning where the creep strains were a function of both stress and temperature. So power law dependence on stress and exponential dependence on temperature. Okay, so and that's what we're showing over here. The creep is increasing as a function of stress and temperature. Well, now when you divide one by the other, the A will still cancel out, but the two other material constants, N and activation energy, will stay in the model. And when you take the ratios and work out the details, it'll work out like this. So the exponential term will give you this ratio, and the stress terms will give you that ratio. So it's sigma U's divided by sigma test raised to the power minus n. N is a material property. And exponential of this quantity, Tu's and T test, that has the activation energy. Okay? So this is how you get the acceleration factors for cases like creep. There are other examples where we have two parameter relationships. For example, electromigration, that is driven by current density and temperature. Corrosion, temperature and moisture. So there are other examples also of this two parameter relationship. So here's one example. Here's temperature and humidity. Okay, so this is time to failure for corrosion, And again, different experts have different models for it. Here's a Nikolai Kudis model. He assumed that time to failure followed a relationship like this, where both temperature and humidity had an exponent, or rather there was an exponential dependence on both temperature and humidity, or rather the reciprocal of those values. And if you were to do an acceleration factor for that, that would look something like this. So e to the power EA over KT plus B to the, plus B divided by RH. So this would be time to failure in use divided by time to failure in test. So this would be TUs, RH in use condition, and this would be T in test condition and RH in use condition. So that's just that ratio. You'd subtract one exponent from the other, and that would be the, so nothing cancels out over here, okay? So if you had a leading order, a leading coefficient here, that would cancel out, but A and B would, activation energy and B would remain. Since you have two different stresses that you're using, there'll be a minimum of two constants. Another version of corrosion model that's very commonly used is the Peck relationship. So there, the assumption is that there's a power law dependence on relative humidity and exponential dependence on temperature. And then this one looks very much like our creep model, like this model. So the RH ratio is raised to a power, and the temperature has the usual Arrhenius relationship. So these are just examples of the kinds of semi-empirical simple design models that people use in the literature, and you can use those to get acceleration factors. Okay. Here are some other mechanisms that we saw. NBTI, which is basically cold holes being transported, leakage in your oxide layer from cold holes, whereas this is from hot electrons, high energy electrons, hot carrier injection. And then the other one we had seen was time-dependent dielectric breakdown. And there, I had said at that time that there are some simple empirical models that are in the literature. Again, there are many models, depends on which researcher you're talking to. But here are some simple examples. So by now you're starting to get the feel. So typically these are exponential. This one has exponential dependence on voltage. It's very much like this model, okay, that we had seen here, very much like that model. And here's a different one for time-dependent dielectric breakdown. You have exponential dependence on temperature, but it's complicated. There's an exponential dependence on temperature squared, and a power law, the power law exponent is also temperature dependent. So it gets complicated. So there's a power law dependence on voltage, and that exponent itself is temperature dependent. So this model gets a little bit complicated. Okay. Again, there are other slightly simpler models in the literature for these. And then finally for NBTI, for the cold holes, you've got a two-term model over here. So you can see there's tau1 and tau2 are model constants. B1 and B2 are model constants. T is the time to failure at different voltages. Okay? So you'd have to solve this model backwards to get the time to failure. And then again, another simple one, power law dependence on voltage. Well, the reciprocal of voltage, and an exponential dependence on temperature. Okay? So those are typical models for time to failure in cold holes. Okay, dendritic growth. Again, there are models for dendritic growth. So I'm just going through a smattering of examples. We talked about dendritic growth in capacitors. We talked about dendritic growth in batteries. And there are simple models. The detailed physics are extremely complex. Remember I told you we use Nernst-Planck equations with moving boundary nonlinear analysis to really solve for the time to failure. But people have built some simple closed form semi-empirical models to fit to those results. And here are the kinds of models that get used. So again, you can start to see a pattern. There's a term outside the Arrhenius term, and then there's an Arrhenius term. Okay, these are all dependent on temperature, so there's an Arrhenius dependence on temperature, and the voltage gradient across the cathode and the anode makes a difference, so that's over here. This one gets a little more complicated. there's a relative humidity term over here and a voltage-driven term over here and a temperature-driven term over here. So it gets complicated over here. This one is, again, Peck model. That's also used not just for corrosion, but it's also used for dendritic growth. So dependence on relative humidity, dependence on voltage, and dependence on temperature. Okay, 3 different drivers: humidity, voltage, and temperature. Okay, and so on. So in the interest of time, I'm going to skip over those. There are quite a few models for dendritic growth that dominate in the literature. Okay, let's talk about another model. We've talked about this mechanism. This is conductive filament formation. Like dendritic growth, this is metal migration. The difference is this one grows from the anode to the cathode, whereas dendrite growth, these are growing from the cathode to the anode. Okay? They're all coming from, the metal is all coming from the anode, but this one, the metal goes to the cathode and grows backwards. In the other one, conductive anodic growth, it grows directly from the anode out. Okay, so here we use, again, the empirical models are over here. So the empirical models look a little bit like this. Time to failure has geometric parameters. So this has to do with what's the separation between the metalizations that are acting as anode and cathode here. So what's that distance of separation? And the reason there's an L effective is it depends on the geometry. If there are 2 parallel traces, L effective is just the physical length. But if there are bends or there are vias, then there are some adjustment factors, geometric factors that are used to estimate L effective. Okay, then these are model constants. AF are model constants. N is a model constant. V is the voltage gradient across them. M is a model constant. And M is the moisture content over there in grams of moisture per unit volume. And it turns out that you don't get these filaments forming below a certain threshold moisture content. So that's the threshold value. So any moisture content above the threshold value will cause migration. So time to failure is given by that relationship. So it's inversely proportional to voltage raised to the power n, inversely proportional to moisture content, and these are all geometric factors. So if you talk about an acceleration factor, these don't change from test to use condition. Those are just geometry of the model. What changes is the voltage and the moisture content. So the product of voltage to the power m and moisture content, you take the ratios of those two between the test and the use to get the acceleration factor. Okay, so that's another example. And that's pretty much it. So those are smattering of different examples of failure models and acceleration factors that go with them. Let's talk a little bit about how to inject our statistical considerations into these models. So think about how to make the model stochastic, because these models are just deterministic, right? If you think about this model that says time to failure is a single value. Depending on temperature and relative humidity, you'll come out with a value. There's no distribution in there. So we have to inject that distribution, and that's done over here. So what we do is we look at the Weibull distribution. This is the Weibull probability density function of the Weibull distribution. It's a 2-parameter Weibull in this simple case. That means gamma is 0. So you see there's no gamma. There's just eta and beta. And so now it's what we do is we take the Weibull eta, which is the Weibull mean characteristic life, and we use the physics of failure model to describe eta. So as an example, if the test is getting if the failure is getting accelerated by temperature, it responds to just temperature, then you take one of your temperature models. So this could be Arrhenius dependence on temperature, and you say that your characteristic life is dependent on temperature. The beta does not change with temperature. So wherever there's an eta, if I substitute back this temperature dependent function, then that gives me a stochastic physics of failure model. Now I get a full distribution. So if I use this model and plot it at different values of temperature, 406, 416, 426, I start to get these distributions at different temperatures. And you can see that the mean time to failure keeps changing as the temperature gets smaller and smaller. Okay? So this now becomes a stochastic physics acceleration model. Okay, another thing to remember is confidence bounds. So why do you need confidence bounds? Well, you are assuming that you know these parameters, C and B and beta, you have complete knowledge of it. In reality, you don't know it that well. You know it approximately, but there's levels of uncertainty in what the true values of those constants are. And why is the uncertainty? Because you extracted these from experiments. When you ran the experiments, you had a finite sample set. If you had an infinite sample set, you would know the exact values of those parameters. But you don't. You took a limited sample set, maybe 20 specimens or 30 specimens, and you ran a limited sample set test and you extracted the constants. What if you were to repeat that test, identical test with identical specimens the next day with another 30? You would get slightly different, similar constants, but slightly different. So there'd be distribution in the constants themselves. So that's why there's a level of uncertainty in the constants. So that's why you need confidence bounds around them. So it turns out that if you know what the sample set is, there are equations that you can use to calculate the confidence bounds around your Weibull distributions. So there are confidence bounds on the Weibull mean, on the etas, which means there are confidence bounds in the C and B, okay? So you can actually generate these confidence bounds if you know your sample size. There are well-established methods to do that, okay? Okay, we already talked about the fact that so these accelerated tests are used at 3 different stages: engineering verification, design verification, and process verification. I won't revisit that. But let's take one example end-to-end of designing and setting up and conducting an experiment like this, accelerated test. So this is an example of EV testing that we did many years ago back when flip chip on board was brand new. So this was a company sponsor we were working with who had not fielded that technology yet, but their R&D group wanted to evaluate that technology, flip chip directly on board, and you know that what drives it is cost. So people went from expensive substrates to just putting the die directly on your circuit card to minimize cost, flip chip joints. So this company wanted to evaluate how robust that technology is going to be. Back then it was just a proposal. No one was using it. I'm talking about early 90s, okay? So what we did is basically designed a test and verified whether it's going to be robust or not. So here's the story of what we learned. So whenever we design and conduct accelerated stress testing, it's always a 5-step process. The 2 dark gray boxes, the 2 yellow boxes, 3 dark gray boxes and 2 yellow boxes. 5 steps, and I'll explain all those 5 steps in a minute. The rest are inputs and outputs, okay? And I'll give you a graphical version of that also in a minute. So the steps go like this. We first look at the design, capture that in make a physics of failure model of our design. We apply stresses in that model, so this could be a computer simulation, okay? Apply the stresses, and we let the model tell us what the expected time to failure is, okay? Then we design how we are going to accelerate the tests, accelerate the stresses, what kind of test specimen we are going to use, how we're going to fixture it, what sensors do we need, so that's all the test planning, how we're going to define failure, how we're going to collect failure data. So we do all the test planning and before we do the actual testing. And then we do some preliminary verification, because remember we did some modeling initially to estimate time to failure, and this, by the way, is estimate of time to failure in the field condition, not in the test condition, okay? And here we are basically trying to just run some preliminary exploratory tests. This is not the accelerated life test. This is just to characterize the specimen, make sure that the initial models that we developed were meaningful. And I'll give you some examples of what we mean by that. And then we repeat that model, but now under the test condition, accelerated test conditions that we developed in our test plan. And so we look at time to failure in the field condition, then we use that same physics of failure model to find time to failure in the test condition, and the ratio of the two gives me acceleration factor, okay? And then we actually go ahead and run that, physically run that test and see actually how many cycles, how much time it took to fail, see whether it got close to our virtual test prediction or not, and then we multiply that result, measured time to failure, by the acceleration factor, and that's our best estimate of how long it's going to last in the field. That's how we qualified or verified new technologies. So let me walk through this example. How did we go through those 5 steps? So So this is the technology we were looking at. This is silicon chip, flip chip directly onto a printed circuit board. So big CT mismatch. We talked about that before. So obviously the solder joints are at risk. So this is 3 parts per million per degree C. This is 17 to 20 parts per million per degree C. The solder joints would get crushed in no time. That's why we use the underfill to reinforce the joints, right? So in this particular study, what we were really doing, but when we say we are verifying this technology, we were trying to evaluate whether the underfills would give it sufficient robustness and which underfills would work well, okay? So, and here you can see some failures. Oh, I apologize. This particular one is not, this is not the thermal cycle. We have a thermal cycling example. This particular one is not a thermal cycling example. This is under moisture and temperature. So under temperature and humidity, these also fail. Why? Because the underfill, and we talked briefly about it when we talked about underfills. The underfill absorbs moisture and swells. And at temperature, so we talk about temperature and humidity. So over time, at temperature, the solder joint intermetallic layer degrades. And in the meantime, the underfill is absorbing moisture and swelling. So the underfill is pushing up on the solder joint is degrading. Eventually, the strength of that solder joint drops below the stress that the underfill is applying, and it fails. So the wear out aspect of it comes from how much time it takes to build up stress due to underfill swelling versus how much time it takes for the solder joint strength to degrade. When the two meet in the middle, that's when failure happens. And you can see some examples of failures. These have cracked under temperature humidity tests, okay? And these almost always fail at the intermetallic because it's a degrading, aging intermetallic that's responsible for the failures. So these schematics are basically showing the forces that are acting on that joint. Because of the swelling of the underfill, you're getting forces in the vertical direction and some forces in the horizontal direction, and that's what's failing the underfill. So how did we conduct these tests? So let's skip over that. So what we did is, first we, in discussion with the sponsor, we decided approximately what the use condition would be. The real use condition is different. They won't allow me to share their real use condition with you. So this is just something we agreed with them to use for demonstration purposes. So we are assuming in this example that their temperature in the field condition is 35 degrees C and humidity is, relative humidity is 85%. So that is their life cycle loading, okay? And it's a constant temperature, constant humidity loading. So of course, in order to then create a computer model of that and mimic this environment, we had to make a computer model, you need to know all the dimensions and you need to know all the material properties, relevant material properties. So we went ahead and figured out what are all the material properties, okay? There's also what's not listed over here are moisture absorption coefficients, moisture swelling coefficients, and so on. One moment, give me a second. Yeah, okay. So then we designed test specimens. So we came up, well, in conjunction with the sponsor, came up with test boards. Let's zoom into that a little bit. It's worth discussing this one. So the test boards look like this. So these are simple printed circuit boards with bare die, flip chipped and soldered down to bond pads. 2 different die sizes, 5 by 5 millimeter and 10 by 10 millimeter. There are flip chip bumps under them. You cannot see them from this side. This is the back side of the die. And there are various underfills inside. So we were studying some specific underfills. So those specific, so some boards had underfill A. I'm not allowed to name the underfill. So some had underfill A, some had underfill B, and some had no underfill at all. So the no underfill at alls we used only for thermal cycling testing, because if there's no underfill, there's no question of swelling of underfill and applying stresses. So for this study, the no underfill boards were not necessary. But for thermal cycling, we had some boards that had no underfill. So today, I'm not talking about the thermal cycling part of the study. I'm only talking about the moisture humidity part of the study. Okay. Okay, so basically we, and these are all daisy chains, so we could model, so we could monitor in real time while the specimen was being stressed in the temperature humidity chamber. We could monitor in real time whether the joint had failed or not, because these are all daisy chain and we were monitoring them in real time. Okay. Okay, so in order to build our models and characterize the boards, we had to know at what rate were the solder joints. So we had to know at what rate these intermetallics were degrading, okay? So that's part of an input information. So we had to run some auxiliary tests, characterization tests, in order to establish that. So what we did is we took some silicon to silicon bonded specimens and then aged them to age the intermetallic layers. And at periodic intervals, so we put a dozen specimens like this in the test chamber. After 10 hours, we pulled some out, tested the pull strength. After 100 hours, we pulled some out. After 1,000 hours, we pulled some out. So basically, at periodic intervals, we pulled specimens out and measured the strength to see how the strength was degrading. So basically, we put them in specimen holders like this. For some, we did a pull test, and for some, we did a shear test. So pull test was being pulled in the vertical direction. Shear test was being pulled in the horizontal direction. Okay. And these were the flip chip dies, and we just bonded die to die, because here all we wanted to know is the intermetallic strength. We just bonded die to die and pulled them apart. Okay. Okay. And here's what we found. So there were two sets of tests, as I said, pull tests and shear tests. So for pull tests, we found that initially they strengthened a little bit. So this is time in hours. So we pulled out at 50 hours, 100 hours, 150 hours, 200 hours, and so on, 300 hours, 400 hours, 700 hours. And what we found is initially the joints strengthened, but eventually the strength started to drop. That's in pull test. And for shear, there was a very small strengthening initially, and then it decayed. But the decay was not as strong in shear. In pull strength, it decayed very strongly. And then we also, those failed specimens, we looked at them very closely, and here's what we found. So the first failures, the initial failures at time 0 and time 50, were in the bulk of the solder, not in the intermetallic layer. And then slowly it started to move into the intermetallic layer. These failed in the intermetallic layer. So initially, as it moved in the intermetallic layer, it strengthened. And then as the intermetallic continued to degrade, it started to drop. Okay? And ultimately, at the very end, the intermetallic all got, the copper all got consumed, because as the intermetallic grew at temperature, as the intermetallic continued to grow, it continued to consume the copper until at the end, all the copper is gone, and it failed between the intermetallic and the aluminum metallization that was underneath. So by then, the strength has completely become unacceptable. Okay? So that's just material property that we're going to use now in our modeling. Okay. Okay. Then for the accelerated test, we picked two different conditions, 85-85 and 120-85. Question is, what's the acceleration factor for these? I'll show you how we calculated those. And both sets of tests were run all the way to failure, so you can see the failure distributions. Here's the failure at 120-85. They failed pretty fast. By the way, we did not run these tests. The sponsor ran these tests. We did all the modeling and the characterization that you just saw. So at 120-85, it failed pretty fast. 85-85, it took more time to fail. And remember I said there were two different underfills. So the two different underfills had two different times to failure. So one was slightly better than the other in terms of moisture resistance. So underfill B with the black circles was better than underfill A with the white circles. Okay. Now, these are the typical kinds of failures we saw. So most of them were in the intermetallic layers. Some were close to the interface between the copper bond pad and the intermetallic. Okay? None of them were in the bulk in this case. All right. So, and these are just some zoom-ins of those regions. You can see there's, in some places they've deviated a little bit into the bulk of the solder along grain boundaries, okay, along grain boundaries, but most of them are close to the interface with the intermetallic. Okay, this is just a zoom in of the data I just showed you. This is at 85-85. This is at 120-85. So these are two different accelerated tests, because remember the use condition is only 35 degrees C. So both of these accelerated stress tests. Okay, so then we started to do the modeling to try to understand what the acceleration factors for these are going to be. Because again, what the sponsor finally wants to know is, here's the test data I have. Tell me if this is good enough for my field condition of 35-85. That's what they want to know. So we want to know the acceleration factor. That means 1 hour in this test represents how many hours in the field. That's what we want to know. Okay, so we ran, for the first part is the stress analysis. The stress analysis in this case is absorption of moisture and the swelling of the polymer as a result of moisture ingress. So what all do you need to know? You need to know the moisture transport properties of this polymer. And moisture analysis, by the way, moisture diffusion analysis, very simple equation, same equation you folks solve in linear heat conduction. It's just the heat equation. All you do is change the variables from thermal flux to mass flux and concentration gradient to temperature gradient, and it's exactly the same analogy, same differential equation. In fact, we even use the heat module of the FEA to solve it. We just changed the variables, and that's all we did. Okay, and here you can see the moisture concentration slowly. So these are intermittent snapshots at different times. So this is at one particular time. You can see the moisture gradient. Slowly the concentration in here gets higher and higher as more and more moisture permeates through over time, diffuses through over time. And as the concentration here increases, all of this is absorbing this moisture and swelling. As it swells, it's pushing upwards on the die, and the solder joints are trying to hold the die back, and they're under stress. The solder joints are under tensile stress. So that's the basic problem here. So what we have to do is find out how much time it takes for the moisture to get in. So how do the stresses grow over time? And how does it? So basically what is happening is you already saw that the strength is decreasing over time. That was up here. You saw that the strength was decreasing over time. And because of the slow moisture absorption, the stress is increasing over time. Okay? Stress is increasing over time. Strength is decreasing over time. Question is, when do they intersect? That is time to failure. Right? So that is what we are trying to predict through the modeling. Okay, so this is the same data. Okay, this is this data, but plotted on a log scale. That's why it's looking a little bit different. So this is strength, but time has been plotted on a log scale. It's been compressed. Okay. So what we did is we took this data that we had and we scaled it by temperature. So we had these tests were at room temperature, but luckily for intermetallic growth, there's very rich literature on dependence on temperature, how intermetallic growth depends on temperature. So we were able to scale these to different temperatures using those activation energies that's in the literature for intermetallic growth. So we were able to scale these strength curves to different temperatures. So here's what that scaling looks like going from room temperature to 85 or 85 degrees C. And here's what it looks like going to 120 degrees C. So you can see that the strength is degrading earlier and earlier because of the activation energy of the intermetallic growth as you raise the temperature. So that's the decreasing curve. I now have to superpose on this the stress curve. So this is the strength curve. I have to superpose on this the stress curve. Okay, so this is just some details of the more details of the moisture absorption analysis. This is the moisture-induced swelling. So the polymer will swell because of moisture content, and this is the coefficient of hygromechanical swelling. Okay, so just as temperature causes expansion by alpha delta T, moisture causes expansion by beta times M. M is the moisture content. Okay. Okay, so here's what the end results look like. So here is the strength curve that we scaled from our measurement by using the activation energy of intermetallic growth, scaled it to different temperatures. And here is from this finite element modeling our prediction of how the stresses grow at different temperatures. So remember, as the temperature changes, the moisture absorption rates will change because all the diffusion coefficients are temperature dependent. So we have the diffusion coefficients programmed in here as a function of temperature. And so that's why the stresses in this region, the stresses at the top, are growing as a function of time as more and more moisture comes in and the polymer swells. But the curves are different at different temperatures because the moisture absorption coefficients are different. So here is the curve at 120, 85. Here is the curve at 85, 85. Okay. And because the polymer has some amount of stress relaxation in it, the curves also start to drop a little bit. Okay, so it grows. There are two mechanisms. One, the incoming moisture is trying to increase the stress. The stress relaxation is trying to drop the stress. The net result looks something like this on a log scale. And now let's start to look at the intersections. The intersection here is at time of prediction. This is our prediction. At 120, 85, the the intersection is at 153 hours. At 85, the intersection happens at 2300 hours. And if you look at the experimental data that was here, this data, if I superpose that data on top of those predictions, here's where they are. This one is the data, the pink one is the data at 120 degrees C. That's this one, this Weibull graph. And the other one is in blue. So here's the data, failure data at 120 degrees C, Weibull slope. And here's the Weibull failure data at 85 degrees C for one of those two underfills. Okay? And so the Weibull mean for those Weibull curves from the experiment was 170 hours for at 120 degrees C and 2600 hours in at 85 degrees C. And our corresponding predictions were 2300 hours for this one and 153 hours for this one. Not a bad comparison. This is another group of researchers who were using the same data but building a more empirical model, and their empirical model didn't do too badly, came up with 170. So they actually calibrated their empirical model to the one data point, and then used that to predict what will happen at the other data point, and they came up with 1750. So the acceleration factor they got between 85 and 120 was 10. The acceleration factor we got between 85 and 120 was 15, and the actual acceleration factor from the test turned out to be 16. So that is actually not bad at all. Neither one is that bad. We live with that level of uncertainty in acceleration factors all the time, and that's close enough that we declare victory. We say, well, we like this model. This model seems to be reasonably realistic to try to predict what's going to happen in the field. So this is basically to check the validity of the model. Ran 2 different accelerated stress tests to check the validity of our modeling method. And now we're going to use this model, because we now have some confidence in it, to predict what's going to happen in the field, which is 35 degrees C. Okay, so these were at 85 degrees C, 2 accelerated stress tests at 85 degrees C and 120. Now we'll use this model to predict what happens at 35 degrees C. So let's go there. So we repeat that same modeling, except now at 30 degrees C. Now the moisture absorption rate is very slow. Degradation rate also will be slow, because at 30 degrees C the intermetallic doesn't grow that fast. So both get extended. The degradation is slow, the moisture absorption is slow. So time to failure should be much higher. So repeat exactly the same steps. And since all of our model constants are temperature dependent, the moisture absorption coefficients and everything, and our stress relaxation models are all explicitly temperature dependent, so it automatically takes care of the fact that at 30 degrees C the stresses will build up more slowly. And here's what we found. So the strength degradation data, when scaled by our activation energy to 30 degrees C, moved over here. That's the green line. And the model, this model at 30 degrees C, this was the degradation curve. I mean, because this was getting so crowded, I just showed the last part of the degradation curve. It builds up from here and eventually comes here. And the intersection point is basically over here. So our prediction is that time to failure at 35 degrees C will roughly be over here, okay? Which is, the prediction is about 28 years. In the field, it'll last 28 years. The other research group predicted about 36 years. We don't know which one is right. We don't have field data at that field condition. But these are predictions, and the confidence we have in that prediction is only based on the confidence we have on the 2 accelerated, the agreement we had in the 2 accelerated stress tests. And these accelerated test data were provided to us by Philips, who was sponsoring that study. Okay. This was actually Philips' research group in Netherlands, Eindhoven. Okay, so that's it. That's an example of how we can combine accelerated testing with physics of failure-based modeling to try to get an assessment of how robust your product is. So is 28 years good? More than adequate as far as this sponsor was concerned, because they were going to use this in consumer electronics. That's why they were trying to reduce cost, because they're trying to put flip chip on bare board to reduce cost, because they wanted to put this in consumer electronics. If you open your cell phones today, you'll find flip chip on board technologies in a lot of them. But they're, of course, all underfilled. Okay, these are also all underfilled. And these were the ones where we learned some of our early studies of underfills that don't work very well, underfills that were leaving voids, underfills that were not flowing properly, underfills where the particles were settling. So these are the studies where we learned all of those lessons. Okay. So in other words, what we did find is that if you look at the mean time to failure, it's not a bad result at all. But if you look at the Weibull slopes and you try to predict the early failures, those were failing pretty early. And the sponsor was not at all happy with that. Why were those? So if you apply the same acceleration factor to the early failures, you find that it's barely 2 to 3 years. And that's definitely not enough for the sponsor's requirement. And the reason they were failing so early is that these Weibull slopes are too low. That means that variability is way too high. Okay? And why is that happening? Because the underfills were not very good. So the worst case filling was far worse than our best case filling specimens. There was a lot of piece-to-piece variability in the underfilling technology. So that's why the end result of this was the sponsor went back to the underfill manufacturer. They re-engineered the underfills quite a bit because they said, look, intrinsically, this is capable of a lot of life. I mean, my better pieces are lasting forever, but my early pieces are not lasting long enough. That's the problem. So it's the variability that's a problem. Give me more consistent quality, and then I can have an acceptable technology here. So that's basically where this study ended. Okay. Okay. I'll end this session over here. Any questions about this? Maybe I'll spend a little time on this slide. So how many of you have heard of the term, especially I'm looking at the people who are in industry or Anandaroop, term stress screening, accelerated stress screening or highly accelerated stress screening or ESS, environmental stress screening, right? What does that mean to you? What do you understand by stress screening? Yeah, okay. I mean, it's different people mean different things by it. That's why I'm asking. One version of it, depending on who you talk to, you get different answers. One version of the answer is whenever you have quality issues, like all these premature failures, these are the failures I'm designing for, right? I'm not panicking about these failures. That's failing when it's supposed to fail. These are the premature failures, and we don't like those. So in the low volume industry, high-rel low volume industry like defense electronics, what the buyer comes and tells the manufacturer usually is, look, these are happening because you've got a process that's out of control. You've got all these manual operations, especially in low volume. There are a lot of semi-manual, non-automated processes and almost by definition, there's a lot of piece-to-piece, operator-to-operator variability. Morning shift, I was sleepy, I produced a bad part. Afternoon shift, I got sleepy again, I produced a bad part. In between, I made some good parts. And the buyer says, no, I don't want the bad ones, I only want the good ones. How are you going to know which are the bad ones and which are the good ones? So they say, well, all right, run a stress test. The bad ones are going to fail, I'll buy the good ones after that. Right, so give me the ones that survive the test and the ones that failed. Yeah, that's where the term screen comes from. I'm using the stress test to screen out the faulty ones and ship the good ones, right? So that's the concept behind stress screening. And it works for certain cases. So the very early failures, which are the gross defects, yes, those you can probably stress and remove very easily. But something that's out here, for example, okay, this distribution, that would be very hard for you to stress screen out because you would have to damage the part all the way until here to fail these guys. Think about what happened to the good guys. You took away that much life out of the good guys, there's only this much life left in it, right? So that's no good. So a part that initially had been designed for, let's say, 10-year life, now barely has 2 years of life left in it because you consumed 8 years worth of life in the accelerated stress screen. So screening, therefore, has become a very loaded term. You got to be careful that you're not over-screening it and removing too much life out of it. And there are known documented cases where this has happened. There are some famous NASA failures that were later on root caused back down to excessive screening. So NASA said, I'm going to buy 3 parts from you. The manufacturer made 10. They screened, and the 3 best survivors they gave to NASA. Except they had screened for so many weeks in order to find the 3 survivors NASA said test till 7 fail. I want only 3, the best 3. And they kept testing till the 7th one failed. By then they had taken out so much life out of the remaining 3 that after they were fielded, NASA was able to launch them fine, but it didn't finish the mission. These were satellite missions. The satellites were meant for 20-year life, barely lasted 6 or 7 years. Okay, they'd removed too much life out of them. So these are very early on. I mean, people have learned their lessons since then. So now screening is done in a far more controlled manner, and there are very strict recipes about when you can screen, when you cannot screen. You will never see screening in high volume unless I get a known defective batch that's been shipped by some supplier of a part or a subassembly, and we discover, oh, there's a problem in it. We sometimes screen those if there are non-stress type of screens available for it. So visual inspection, bad piece, good piece, there's no stress, that's fine. Or just a functional test without applying a lot of stress, just a functional test. Oh, this one is out of spec, bad, good within spec, I'll take it. So non-stress screens are allowed. Stress screens, people have become very, very nervous about it. Even non-stress screens, it means you're going to handle all these parts. And handling damage alone can sometimes ruin the reliability downstream. Okay? So all of those are big problems with screening. So screening, people say, loosely speaking, people say, oh, that's a 2 sigma process. Have you heard, oh, I have a 6 sigma process? Have you heard that term, right? The rule of thumb in that community is that screening is just a 2 sigma process. So if you're screening your parts, don't claim you're a 6 sigma organization. You're a 2 sigma organization, no better, okay? Okay, now, so here's the common sense. I mean, quantitatively, it's way more complex. You have to do a lot of calculations. But qualitatively, the common sense version is this. If you have multiple distributions in your population, that means you have a main population that's good, those are these guys, and you have a separate subpopulation that's bad, that's any one of these guys, okay? Then you stand a chance that you may be able to design a screen to get rid of the red population and then ship out the blue population, provided the red and the blue are sufficiently separated. That means there's a sufficient separation between this subpopulation and the main population that if I screen long enough to screen out these bad guys, I still have reasonable amount of life left. But if there's not enough gap left between them, that means this one and the main population, you can't screen that out because by the time you remove all of those, there's no life left, very little life left in the good part. Everyone understand that, right? Okay. There's another example of poor quality. So that's one example of poor quality that you cannot screen out. If the subpopulation and the main population are too close, you cannot screen them out. If they are sufficiently separated, yes, then there's a reasonable chance. You would do a lot of calculations to see how much gap is left in there. You would be monitoring the failure rates very closely as you go because there's a decreasing failure rate. As soon as that stops, you stop your accelerated testing. So there are some very complex guidelines on how to do this in a real world. Okay, I'm just giving you some high-level guidelines here. There's another situation of poor quality where you cannot screen at all, end of story, and that's over here. Think about these two populations. So these are two versions of the main population. In one case, you have an acceptable main population. In the red case, you have an unacceptable main population. That means this is what I produced on day 1. This is what I produced, let's say, on day 2. For whatever reason, on day 2, all my pieces came out with wide variability. There's no subpopulation there. The entire population came out with wide variability. Okay? The question is, can I screen out the day 2 population to only pick out the good pieces? Because there are some good pieces in there. Look at how long they live, some of them. The problem is some of them fail too early. Can you screen the bad guys out over here? Let's say I test until here and at least get rid of the absolute worst guys. Can I ship out the rest? Think about the ones that are remaining, right? Yeah, think about the ones that are remaining. So I have, no, not just quite a bit. It's worse than that. So I have screened out everything until here, okay? Now the next guy to fail is the next one in that distribution. How much time does he have to fail? 0. From day 1, I'm going to have failure rates in the field and a rising failure rate in the field, right? Absolutely unacceptable. So unless you have reason to believe that your quality issue is a multimodal distribution and not just a wider unimodal distribution, you can't screen. So some people will tell you, where's your proof it's unimodal? If you can't prove it's unimodal, I'm not going to let you. So the buyer will come and say, no, I don't want to buy anything out of it. So usually there's negotiations and haggling that goes on. You have a bad lot. Buyer says, oh, you just sent me a bad lot. I just inspected some and I got some failures. So the seller comes and says, oh, don't worry, I'll screen these out and I'll give me back everything. I'll screen them and I'll send you the good parts. At my cost, I'll do it at my cost. Buyer will say, no, you can't screen it. First, prove to me it's multimodal. If you can't prove to me it's multimodal, I'm not buying anything from you, right? Because there's no guarantee that you don't have this kind of a distribution. And if you do, then after screening it, you just made my life much worse, the buyer's life much worse. So buyer's going to have very high failure rates in the field. So at least in the beginning, they would have started out with a low failure rate, but now they're going to start out with a much higher failure rate. Buyer doesn't want that, okay? So unless there's reason to believe, and for that you'd have to go back to the manufacturing process, you'd have to root cause, you'd have to convince the buyer this is where the defects came from, and look, that was only one shift. The rest of my pieces are all likely to be in the blue curve. That one shift would have produced a few bad ones. Let me screen those out. And here's my proof that there's sufficient life left after the bad ones go. Unless you can answer all of those questions, the buyer will not let you screen it. Okay, so that's how screening works now. So, okay, I think that's 4:20. We should probably stop over here. Let me just pull up a few slides by way of summary. Okay, so thanks for sitting through 5 grueling days. So to end, I just want to circle back and close back up on everything we've talked about. And everything we've talked about really can be summarized back by this bubble chart. So we started to get a flavor for what we mean when we say, what's in the body of knowledge that we call physics of failure. What are failure mechanisms? What do people use as models to fit to these failures in the field? What drives them? What kind of stresses drive them? What kind of material properties do you need to describe these, to put into these models? What kind of stress analysis do you need to use these failure models? Where in electronic systems do they occur? We spent the last 5 days getting a flavor of that. The devil is always in the detail, and we haven't even been through any of the details. I've given you a very high-level overview of everything. The real life is complicated. Using these is not that easy, not that simple, but people do it, okay? So people do it. Engineering is detail. The success of engineering lies in how you address details, okay? And that's what people do. They get down into the mud, get their feet wet, and actually learn how to use these physics-based approaches. Then we talked about the fact that, well, it's so tedious trying to use this physics of failure-based approach. It's so detailed and so tedious that there's no way you can do this by hand. You need tools to do it. So there are software tools that people use, and the availability of these kinds of software tools is steadily increasing out in the market. More and more people are marketing software tools like these that will help you implement these physics of failure approach in a more automated manner, so the computer does all the analysis for you and gives you back answers of dominant failure modes. You as an engineer or any analyst knows that your responsibility is finding reliable inputs to put into the model, right? As Anandaroop said, garbage in, garbage out. So if you put in bad inputs, you get meaningless predictions. So your job is to find right material properties, put in the right stress conditions the product's going to see, put in the geometries, reasonably a good description of the geometry of your product, and then do reliable stress analysis, and then you should get reasonable predictions. We also learned that the world of accelerated testing can benefit a lot from these models, because you can actually quantitatively predict acceleration factors at different stress levels as you raise the stress levels based on the models that we use in the physics of failure world. I haven't talked at all about, except in a just storytelling qualitative sense, I've talked a little bit about PHM. That's another huge research area. Almost 1/3 of our center really is doing this. The remaining 2/3 is doing all the remaining bubbles put together. Okay, so that's a huge research area, rapidly growing because the power of data analytics is growing so rapidly that we are benefiting more and more from that. So we are just bringing the physics of failure part to the table, and we are joining hands with the data analytics world to do combined fusion prognostics. And that world, the data analytics world, is growing so rapidly, becoming so powerful, that continuously our approaches are being modified based on that. Okay, I talked about supply chain assessment, and that's Obviously, this kind of a detailed, knowledge-based approach doesn't work if your suppliers are not giving you the knowledge, because you're not building all the parts, you're assembling some of them, and you're building the rest of them. The portion that you're building, you have the knowledge. Portion that you're buying, you don't have the knowledge. You don't know what materials, what geometry, what processes were used. You're relying on your suppliers to give you that information, right? So that's why the supply chain interactions are so important there. And that's easier said than done. In the commercial world, sometimes you don't know who your supplier is. You just bought from some distributor over the counter. So high-rel products from reliable companies don't work that way. They're not just going to go to the nearest shop and buy the parts. They have a supply chain they've set up. They have contracts with the supply chain. They exchange information. They pay for that information. The cost goes up. That's why when you buy a lamp from, we were talking as we were walking, when you buy a lamp from Philips, it costs more than when you buy it from some unknown Chinese supplier. There's a reason, because they paid more to get this lamp on the street. And they know a lot more about the reliability of this product than the Chinese supplier who sold you some unknown brand. Okay, and finally, as we said, again, I don't do research in that area, but unless you have effective ways to model the cost of all these activities, you cannot come up with a good warranty plan, warranty policy. So if at the end of the day you want to have the best warranty, and what does best mean? It's got to be more attractive than your competitors and at the same time not lose you money. So unless you know how all of this is behaving, you don't stand a chance of doing that. So the more knowledge you have about the rest of this, the better your models are going to be, and that's where your competitive advantage is over your competitors. Okay, so that's pretty much it. I want to leave you with that slide finally. If there's one slide you remember out of the 217 slides we covered this, I just made that number up. I don't know how many slides we covered, but whatever it is, we covered a lot of slides. Even if you forget every one of the other ones, don't delete that slide. Keep that one, okay? This is what's going to eat your lunch when you start making and building and marketing electronics. So any of you who end up in the electronics, 3 of you already are, rest of you, if you end up in the industry making electronic parts, this is what will eat your lunch unless you're careful, okay? So you got to have some level of knowledge, because this is why your electronics will fail. So this body of knowledge is every day. I want you to get up once and say, okay, this is what I got to worry about, okay? All right, supply chain and everything else we've talked about. All right, if there are questions, you know where to find me, or Professor Bhattacharya knows where to find me. Happy to talk to any of you, okay? This is what we do for a living, and you know how we academics are. We love to talk. So if you have a problem, come on over, we'll talk, okay? All right, thanks everyone for your time, your patience. We'll do a very short exam, okay? We'll do a short break before that? Yeah, let's take a short break, and Anandaroop, can I discuss something with you over here during that time? We need to go off screen.